Carbon dioxide, CO2, is compressed in a piston cylinder assembly from a pressure P1 of 8.8 bar and a temperature of 300 Kelvin to a final pressure P2 of 8 bar. The initial volume is 0.3 meter cubed. The process is described by the polytropic relationship PV to the N, where that exponent N is 1.3. That's equal to a constant. Assuming ideal gas behavior and neglecting kinetic and potential energy effects determined for the process the work, and then the heat transfer using either data from table A23 or the heat transfer using constant specific heats evaluated at 300 Kelvin or using constant specific heats evaluated at 400 Kelvin. So one to calculate the work, but three methods to calculate the heat transfer for this process. And right away what we're going to notice is the answer for part B and the answer for part C and the answer for part D are different, although for B and D they're the closest of the three, and this one is more off, but we can talk about that as we get to it. But let's just solve for part A. What is the work? Well, we're given that it's a polytropic process. We're given the initial volume and the initial pressure and temperature and the final pressure. So what we think about how to calculate this is calculate the work. 1 to 2 would be the integral of the pressure dV from V1 to V2. And for that polytropic process, we've worked this out before. You calculate that the final pressure times the final volume minus the initial pressure, initial volume, divided by that 1 minus that polytropic exponent on the volume. For this problem, that N is 1.3. Okay, so we take a look and we ask ourselves, do we know the initial pressure? Good. The initial volume? Good. We know the final pressure? Good. We know this exponent N. We don't know the final volume V2. So how do we calculate V2? Well, it always behaves as an ideal gas. So P1 V1 is equal to N R bar T1 all the time. You can put that at T2 as well. So what we do is just divide this by T1. And then what we find is that equation is the number of moles times the universal gas constant of the carbon dioxide that's trapped in that piston cylinder assembly is the same from state 1 to state 2. And so using this relationship, just forgetting this in the middle, but you've got the initial pressure, the initial volume, the initial temperature, you have the final pressure, and what we want to calculate is that final volume V2 right here. And so we're left with two unknowns. The other relationship that we can use is that we have the pressure times the volume to the N as a constant. So that constant's the same at P1 V1 and P2 V2 to the N. And so we just forget this constant in the middle. So we just have this equation. We take a look and we say, well, we know P1, P2, and V1. The only unknown is V2. So let's use this equation. So V2 is equal to V1, P1 over P2 to the 1 over N. Substitute numbers. So we'll start at 0.3 meter cubed. And our initial pressure, 0.8 bar divided by our final pressure, 8 bars, so that's what, 1 over 10, to the 1 over 1.3. When you run that calculation, the volume comes in at 0.05104 meter cubed, V2. So now we can go back to our work equation. We just calculated V2, and we calculate the work. 1 to 2 is equal to Now we're going to put our pressure in units of kilopascal and volume in meter cubed, and that will work out nicely to kilojoules. So the pressure at P2 is 800. I'm going to leave the units off just because I don't want to save room. That's kilopascal times our final volume, 0.05104 meter cubed. That will become units of kilojoule. We have the pressure of 80 kilopascal times the 0.3, and we divide by 1 minus 1.3, and the units work out, and we get the work 1 to 2 is negative 56.1 kilojoules. Why is it negative? Well, because it's being compressed. And so from the perspective of the carbon dioxide, it's work into the system, not positive work out. Okay. All right, now solve for the heat transfer in kilojoules using the data from table A23. Okay. So how we do this? We'll write the energy balance, or the first law of thermodynamics, for the process. And we have going from state 1 to 2, and you'll have the final internal energy minus the initial internal energy is equal to the heat transfer in 1 to 2 minus the work out 1 to 2. Okay, so we're looking for Q 1 to 2. The W we just calculated. We have to be able to calculate these changes in internal energy right here. And so the Q 1 to 2 is equal to the work 1 to 2 plus, and there's a couple ways to calculate it. You could calculate it using the number of moles. I know that I'm recycling N. I've used N up here, but N is also used, lowercase n is for the number of moles of the gas, times U2 bar minus U1 bar. What do you mean by these U with the bar on top? Well, that's the specific internal energy, not on a mass basis, but on a molar basis or kilomole basis. So if we look at the units here for this U bar, they're kilojoules per kilomole. Well, where do we get that value? Well, it's a function of temperature, and we get it from table A23. So from table A23. Well, you could also do it on a mass basis, but then all you're really doing is taking and multiplying by the molar mass and dividing by the molar mass. So let me do this. If we put equal to work 1 to 2 plus the molar mass times lowercase n, and then you have U2 bar minus U1 bar, and you divide by the molar mass. Really didn't change the equation, we just put the molar mass in the numerator and in the denominator. This converts to work 1 to 2 plus the mass times U2 minus U1, where what? That's the specific internal energy in kilojoules per kilogram. Well, where do we get that value? Well, we're going to get that value from taking the value out of A22 and divided by the molar mass of carbon dioxide. So to me, you just might as well get used to using this one. Just use the one where you're using the specific internal energy on a molar basis, not on a mass basis, straight out of table A23. Okay, well, what we have to do is, this is a function of temperature. Let me come up here. So we are given T1, and we can get U bar 1 is equal to U bar for the carbon dioxide. Don't get off on the wrong column or anything. Make sure it's carbon dioxide at that temperature 1 of 300 Kelvin. So let's go to the table and do that. I believe that's on the next slide. So yes, we go to table A23, and its title is Ideal Gas Properties of Selected Gases, blah, blah, blah. And I cut and paste and move this information, which is in the header, over so it can be seen. And they're saying that the enthalpy this is H bar as a function of temperature right there. And the internal energy, U bar as a function of temperature right there, are in units of kilojoules per kilomole. So it helps us, be clear what the units are. We come down, we find carbon dioxide, CO2. This information is not needed. We'll get to that in Thermo 2. The enthalpy of formation is not needed. We don't need this information about S bar naught. That would be when we get to chapter 6 with entropy. And we're just focused on either the molar enthalpy or the molar internal energy as a function of temperature, and the temperatures in Kelvin. So we come down here, and there was our T1. So our T1 is 300 Kelvin. We look across, and this is our value of U bar. All right, so it's 6,000. That's a comma, not a period. 6,939. So we can come back here. So that's equal to 6,939. Okay, well, we need to get the T2 in order to get the U bar at 2, state 2. Well, how do we calculate the temperature at 2? Well, we come back to this relationship right over here. And because we had already calculated, we didn't use this relationship for the ideal gas equation in order to calculate V2. We used the polytropic expression to calculate V2. But we can still come back to that ideal gas relationship to calculate T2. And so I'll just rewrite that T2 is equal to T1 times P2 over P1 times V2 over V1. And for this problem, we have our temperature, T1, that's 300 Kelvin. Again, I'm fighting for space, so I'm going to leave off the Kelvin. And we put our pressure, final pressure, 8 divided by 0.8. Then our volume, V2, 0.05104 divided by our initial volume, 0.3. And we calculate the final temperature. T2 comes in at 510.4 Kelvin. So we go back to table A23, and we look down here for, what is it, 510.4. Well, it won't be exactly 510.4. You'll have to interpolate. And since we've done interpolation a number of times, I just leave that as an exercise to calculate that. You find that U bar 2 at 510.4 Kelvin out of table A23 comes in at 13899 kilojoules per kilomole. Maybe I should have put my units up here, kilojoules per kilomole on U bar 1. So we have both U bar 1 and U bar 2, and the only thing we need is the number of moles. Again, I apologize that this N is used for the number of moles here, and then this N is used for the polytropic exponent. But that's just what it is in engineering. Sometimes we recycle them. So how do I find the number of moles? Well, we can go back to the ideal gas equation. Maybe I write it up here, the ideal gas equation. And there's many versions, but the common version, P1 V1 is equal to N R bar T1. So you solve for N, which is the P1 V1 divided by R bar T1. And I'm running out of room, but we put sub numbers in. What's R bar? The universal gas constant, 8.314 kilopascal meter cubed per kilomole Kelvin. Okay, and we calculate the number of moles to be 0.00962 kilomole. All right, you keep more digits in the calculator. You go to the next step where you calculate, I would calculate what is n times u bar 2 minus u bar 1 as an intermediate step. You don't have to, but it comes in at 66.97 kilojoules. And so now the Q1 to 2 is equal to the work. The work we calculated, negative 56.1 kilojoule, plus that 66.97 kilojoule. And so Q1 to 2 comes in at the 10.87 kilojoule. That's our answer for part B right there. So we have the answer for part A, and we use table A23 to get the molar internal energies, and then solve for the Q, the heat transfer. Well, I'm going to continue this problem, and for part C, which is calculate the heat transfer in kilojoules using this constant specific heats. Well, I think what I need to do is probably scroll down, and we'll just write it like this. Okay, so if we're interested in calculating Q1 to 2, the energy balance equation is work 1 to 2 plus that change in the internal energy. I could write it as U2 minus U1, that's fine. But here, what we want to use is our constant specific heat. So that will be either you can put it on a molar basis, that would be like the number of moles since we calculated it. Then we have the specific heat constant volume on a molar basis times T2 minus T1, that works. Or you can put work 1 to 2 is the mass times the specific heat constant volume on a mass basis, T2 minus T1. Okay, where are we going to get this constant specific heat? Well, we'll go to another table. And I forgot to mention, if you need the molar mass of carbon dioxide, go to table A1 and you'll find that it's 44.01. So actually that's what I need right here. I'm going to scroll down again, sorry about that. But we can calculate this mass is equal to the molar mass times the number of moles, 44.01 kilograms per kilomole, times the 0.00962 kilomoles, and we find the mass for this system comes in at 0.42348 kilograms. All right, now let's get C sub V. So C sub V will be out of table A20. We have the ideal gas specific heats for some gases, not all gases. I think there's 6 gases, but one of the gases is carbon dioxide. So we have a column of C sub P, a column of C sub V, and then the column which is K, the ratio of the specific heats. Well, we're interested in C sub V. The units on these are kilojoule per kilogram Kelvin. And we're interested in 300 Kelvin. So this is the value, 0.657. So we go to the table. What was that table? I forgot. A20. And we find C sub V at 300 Kelvin, 0.657 0.657 kilojoules per kilogram Kelvin. All right. So now we can substitute the numbers, and I'll just say that we substitute numbers for this equation right here. And we calculate Q1 to 2 using that constant specific heat at 300 Kelvin comes in at 2.41 kilojoule. And that's the answer for part C. That's a big difference between the answer for part B and the answer for part C. One of the reasons is that when you have a polytropic process and N is getting close to the K value. So let me jump back over here. I hate to do that. You get sick and tired of jumping around. And this K value is in the 1.2-ish, low 1.2s, maybe 1.25, somewhere in that range. What happens is we'll learn from the next chapter, when we get into chapter 6, is that it's like a adiabatic process. It's reversible adiabatic compression. Hence, it's that n exponent is close to the K, the ratio of specific heats. And when that happens, then Q is close to 0. Well, it's not 0 for this problem. It's around 10. But when you are subtracting the difference between the work 1 to 2 is closer to, then let me try and draw it this way. This value for the work 1 to 2 is close to this value, which is the change in internal energy, such that this Q 1 to 2 is small. Well, when they're comparable, a small difference in the estimation of the change in internal energy makes a big change in Q. Well, there you go. Maybe I should have wrote it like this. Maybe I should have said the work 1 to 2 plus U2 minus U1. These are about equal in size and opposite in sign. And when they are, this Q 1 to 2 is small. So any small error in estimating the change in internal energy, this is a cap U here, leads to a larger percent error in Q 1 to 2. So it went from almost 11 down to 2. Well, how do we improve it? It's not that the specific heat, using constant specific heat, is a bad approximation, but what we should do is we should try to evaluate the specific heat at an average temperature, where the average temperature would be the average temperature for that process. Well, it started at T1 and ended at T2, so just take the simple average, T1 plus T2 divided by 2. Well, if you calculate the average temperature for this problem, it comes in around 405 Kelvin. Well, let's round off to 400 Kelvin because that's what Part D asked. Part D says use the constant specific heat evaluated at 400 Kelvin. So when we go to our table, let me go show that. We come down here to 400 Kelvin and we use 0.750. Doesn't look like a big difference, right? So in table A20, 0.657 at 300 Kelvin and then 0.750 at 400 Kelvin. So from table A20, we find the C sub V is 0.750 kilojoules per kilogram Kelvin. That's the only change. The same equation, you have the Q 1 to 2 equal to the work 1 to 2 plus the mass, specific heat, constant volume, T2 minus T1, and we calculate Q 1 to 2 is equal to 10.7 kilojoules for part D. And so it's a lot closer, a lot better match between the most accurate being the table A23 and then using a constant specific heat. Sometimes I'll say this is a warm analysis versus if you use a constant specific heat at room temperature, it'd be like a cold. So there you go. So with that, we'll go ahead and stop this problem.